We'll get started. There's been a whole sequence of technical issues that prior to this, that's why I'm running a couple of minutes late here. And one of those technical issues, some of them point to the possibility of some hardware issue, and one of them is interfering with normal operation here in the sense that Zoom is unable to detect a camera on my machine incongruously. It also looks like there may be some issue with my microphone. So I'm going to be upping this. Okay. So today we're going to be exploring the addition of some discrete event simulation as well as multi-run analytics within for an Asian-based model within AnyLogic. Now, in order to speed this whole process up, I, with some regret, decided to build atop an existing model. So if you go to the course website on either the Fields LMS side or the Canvas side here at U of S, you will find models that we built in class. And one of those models is called Minimalist ABM Neighborhood Mobility V4. We had previously built this in a session, and we're going to be building atop of it within this session. Okay, now I'd like you to load that into your AnyLogics. I'm going to share my screen. And you may recall that this is a model which involves individuals characterized by their okay, the Zoom workplace is closed unexpectedly, but I suppose you're able to interact with me still. So we can characterize individuals as they progress through a natural history of infection. There's also characterization of their mobility, which in principle can bring them to any of several types of venues, including their homes, their workplaces, but also community places. Right now, we don't, in fact, have community-related mobility, but we do have a set of community places. We had previously to this model added some statistics, both at an individual level, such as the cumulative count of infections people experienced, as well as at an aggregate level for this population. We had characterized some of what are termed in AnyLogic statistics, which characterize things like the average infection count and the prevalent case count. Okay, so the average infection count is taking the average over different people in the population of the number of times they've been infected thus far. Okay. Now, we're going to be extending this model in a couple of ways. And broadly, my hope is to get to explore two different types of extensions to this model. Some related to simply reporting on the model with multiple successive realizations of the model, as we spoke about yesterday. This is reflecting the fact that within these models, we have stochastics, and the invariable route that we use to generalize about the behavior of said models and to find regularities within that behavior, despite these stochastics, is to run what are termed ensembles of realizations. So these would involve running a model not once, but many, many times, potentially hundreds or thousands of times, as required to give us requisite statistical reliability in the outcomes of said model. Now, this is closely related to, but distinct from the matter of sensitivity analysis with respect to model parameters, a topic to which we will press ourselves in this classroom tomorrow. For now, however, we're going to be examining how the model behaves as we run it again and again and again with the same set of parameter values. That is, the same assumptions. Same structure, same assumptions, different results each time because of stochastics. And we're going to put in place some mechanisms that will summarize this behavior. Okay. So here I'm going to take this model and we are going to successively extend it, okay, with those mechanisms. So the first thing I'm going to do is go and add a statistic, which is going to be called cumulative infection count. Okay. Oh, I already have one. I'm sorry. I already have one here. Count cumulative infections. Okay. So we already have that. We don't need to compute it at the end. At the end of a model run, this will hold some value that characterizes the number of infections that have occurred across the course of that model's operation, right? Let's run this model. Okay, the plot thickens. Pardon me while I I have to choose my words carefully. So the current situation exhibits unexpected instability, and it presents me with some rather undesirable choices. I can either proceed through this session unable to save the model and unable, therefore, to distribute it to students, or I can engage in a sequence of silicon robbery, which is unlikely to remedy the situation. Or I could build a model from scratch instead of building atop this model. Each of those is encumbered by undesirable characteristics. But choose we must, as choose we can. We live in the strange world of computer and man. Okay, so I think what I will do is close this model and, with regrets, bid it adieu. It's exhibiting a most unpleasant set of behavior. Okay, yes, I'm dealt significant uncertainty here as well. Okay, so you'll have to pardon me while I probe the extent of the current dysfunction. So I'm going to create a model, and I will say my test model 1, and I'm going to set this to days, and I am going to see if I can put into this model, yes, I know. Well, we what we lack in functionality, we make up for in entertainment. Uh, well, I'll be. Press stuff in. This the current situation is characterized by dysfunction at multiple levels, and that dysfunction is causing unusual effects, both visual and computational. But I seem to have escaped from their strictures for the moment, mind you. Let me press myself into my task, and plow on, as they'd say in Britain. Test parameter. This is not how I wanted to spend my session, but it seems that I've stepped forward, I can save the model. So we have enjoy a measure of success. I will now reopen that original model and see if it remains encumbered by its previous issues, shackles, as it were. Okay. Here's the model that I had opened before, which proceeded to cause distress, and I am able to save it with some alacrity. So we are back on track, and we will proceed, and we will take advantage of that by pressing forward. Comforted by the notion that apparently a simple save and close and reopen of the model may be sufficient to unshackle us in some situations, whereas in others of seemingly identical error messages, even rebooting the computer, I can state with confidence, is not enough. So let us stalwartly press on, Shackleton-like, in our exertions. Okay, so we have this model. We are going to go and add to said model. First of all, I'm going to call it version 5. And that's because I will be distributing and I don't want to overwrite version 4. Okay, so we have main. We are going to create a new experiment that is a new sort of meta scenario of sorts. This is going to be a stochastic sensitivity analysis. It is a parameter variation analysis. And we have succeeded in creating that. What did I do? Well, I went to new experiment parameter variation, and I called it stochastic sensitivity analysis. Okay. Here we have the default values of all the parameters, but we've also specified that some number of runs here. I'm going to say freeform. I'm just going to use these default ones. And I'm actually going to run this 100 times, no less, 100. So each run of this sensitivity analysis is in fact going to translate to 100 iterations, or in this case, which translate to 100 realizations of this model. Each of those is going to run from time 0 to time 100 days. And I want to change that. Let's see if I have any. These were simply run at unlimited. I'm going to change this to 365 days. So stop at specified time. This is the sensitivity analysis. Okay. Having done that, let's hew to Jeff McDonald's admonition, and we will run this model. And we will run it when we press run, not once, but 100 times. And you can see my different cores on my laptop are busily engaged in running this model, not once, but 100 different times. And each run is reporting some infection profiles of the population or some occurrence of infection. This was some messages I'd put out to help us understand the model. So we've run it 100 times, but are nary the wiser for it. We have no output from it. It's what we have just performed is full of sound of fury, but it signifies nothing of significance because we can't get anything out. We will now remedy that situation. And to that task, we now turn our attention. Okay, so if you open up this experiment, thus far in this class, in our endeavors, really we've viewed the scenarios as things where the real action is at the parameters. And we may use default values of parameters, or we may have changed assumptions about them, but we're really not taking full advantage of them. We didn't really put things in them. Here, one of these experiments is, in fact, a significant computational entity. It actually is going to run the model, not once, but 100 times, and it needs some way of summarizing the results. It is to that task that we now turn. So if you go to Palette, and you go down to Analysis, you will find that there is, and we've used this before, a histogram data object and a histogram. Not the histogram 2D yet. Histogram and histogram data. I'd like you to pull histogram data in, and this is going to be called cumulative infection count histogram data. This is going to actually hold the values, the bins, and we're going to count the number of realizations, the number of runs of the model where the cumulative infection count has fallen within a certain range, successive ranges in the histogram. So the histogram is going to summarize empirically the distribution of values we're going to get out. It asks us how many intervals. I'm going to say 20 intervals. And I'm not going to be particular about the initial size right now. This is where the real work is done in this histogram data object. But we do need a way of displaying it. And again, we're operating within the confines of this experiment, this stochastic sensitivity analysis. So we're going to go drag this here. This is going to be a cumulative infection count histogram. The title of it, fittingly, is going to be very similar. I'm just going to break it up into separate words. And the so-called histogram is going to be none other than this data object. So it's exactly this data object that we created here, the name of this. Okay. So this histogram is the visual enactment, or is going to display the data within this data object. So it needs to refer to it. And that's what this is. Okay. And if you want, you could have more than one histogram. Data object, data being shown, but we're going to leave it like that. Okay. So we have this pair. Let's make sure it builds. It builds, and it's a computationally happy camera. Okay. Now, we have the vessels to store the requisite data, but now we need to go obtain that data. Right now, we have the ability to display a histogram. We have the display mechanisms, we have the bins and so on, but we actually have to populate them with data. Right now, they're but empty vessels. And we have to make sure that we put requisite data in them such that it could be characterized. So you're going to go to projects. You're going to go to the stochastic sensitivity analysis here. And here, within the Java actions area, that's where the action's at. Java actions of this whole experiment. None other. So of this whole experiment, we will go to the Java actions and properties, and we're going to put something in after simulation run, and we'll put something a little bit further up. So during the initial experiment setup, we're going to go reset this data. Now, if you didn't happen to have it in your clipboard, you could always go and use autocomplete as your friend and reset it. Make sure the semicolon is there because it's a command. We're saying, do it, change this. Okay, it's a statement. Next, after each simulation run, we're going to actually put data into this. This is just clearing any data out that was there before. Maybe I'll put that before each experiment run, just in case we do not close this and we run it multiple times. I'm going to do it before the run, not just when this comes up the initial time. I think that's the difference. Okay. Now, it's really at the simulation run, after the simulation run, that the action happens. Here, what needs to happen is after we run the simulation run, we have to salvage data from the simulation that we've run, from the particular run of main that we've undertaken. We have to get the data out to be displayed, the cumulative infection count. We have to read it out. Are we ready to do that? Hearing no objections, we're going to say we're going to add a value in there. What value will it be? Well, this little light bulb tells us root is referring to main because we just run this run. We have this main that we've run, and main is a thing termed here root for reasons that go back in computer science history into the mists of time. So this is the root. This is the root of the model. Okay, main has within it a bunch of other things. It's kind of the top of the hierarchy, so we'll call it root. And we could refer to things in main here, such as the count cumulative infections that live in main. To what does this refer, this root.count cumulative infections? Well, dear viewers, gentle viewers, it refers to nothing except for this thing. So what's going on is that this stochastic sensitivity analysis is running again and again, main. And each time after the run completes, once the simulation completes, this value will hold the cumulative count of infections that have transpired in said run. And before main is relegated to history, while we've still got a handle on it called root, we could go get the count of cumulative infections from it. And I built it, and we've added it into our histogram data object within this, and it shall be displayed. So let's go see what happens. Let's go run this. My wife is recommended by many virtues, and one of them is that she's a PhD chemist. And she noted to me early on in our relationship that computer scientists are different than chemists. You will never find a chemist uttering in their lab, "Let's see what happens." But that encumbrance is not there for computer scientists in their simulation modeling, nor, I might add, to her chagrin, in their kitchen behavior. So here we're running this simulation over and over again, and we're seeing a singularly monolithic result. It appears that this has been populated indeed by 100 samples, but every one of them carries the value 1. It seems that there's only one infection taking place right now in the default simulation. I'm going to go observe, is indeed that the case? I would have anticipated that this model would actually lead to spread. There's our single person. And no, okay, so we are in fact encountering many people getting infected. In fact, there's some who remain infected yet, afflicted even as we speak in their homes. Okay, so it seems that's not the case. Let's go figure out what's going on. Yes, the old horse knows the way. Don't worry. Under randomness, we need to change this to a random number seed. Now let's run this. We were running it with the same exact random sequence every time. A random sequence in which the maximum number of people infected was in fact 1. But that was not privileged. That was just one particular rendition. Now, if we run it 100 times, we will enjoy a measure of diversity in the results. Diversity that exhibits multimodal character. This is not a unimodal distribution. There is the possibility we'll have but one infection, the initial infective. But it seems that the majority, in fact, tend to fall somewhere upwards of the high 200s and between that and somewhere in the mid 300s. The cumulative number is 300. The mean is 300. If we wanted, we could copy this and we could paste it into a spreadsheet in a spreadsheet package of our choosing. And I will do so in somewhat tempting fate in LibreOffice, which has a bizarre tendency of opening a dialogue in another workspace. Discard all, and yes, I want to discard. Thank you. No, I want to cancel. Thank you. And well, that's not what we're seeking. Here we go. Here we will paste in the data. The fraction of the counts that fall where the cumulative infection count fell within a certain value, between minus 8.6, or rather unhelpful value, to 10.6. And you can see that 4% of them roughly fell there, probably 4 out of 100. But then there was this long valley where there were none. And then the remaining 96% fell somewhere between 298 and 356.2. Okay. So we've just seen some variability in results. What we've just done is to plot out some indication of variability here in the cumulative infection counts. But we can do better. Let's next apply ourselves to characterizing time behavior, summarizing that. So we have a sort of summary of the cumulative infection count. It bears noting we could have called the statistics if we had wanted to, characterizing like mean infected count across the population. But in the interest of making best use of the remaining time, what I'm going to do is instead go to the stochastic sensitivity analysis, and I'm going to go back to this, and I'm going to add in another construct. I'm going to add in a pair, just like we added a pair here of a histogram data object and a histogram. I'm going to add in a pair of histogram 2D data, we're moving up in the world, and a histogram 2D object. This one is going to be called new infections histogram 2D. Now, I'm very sorely tempted to call it incident case count histogram 2D, but with a nod towards potentially broader audience, I'm going to call it new infections. Okay, now we'll go and see how how further options on this will be useful to us. But for now, I'm just going to leave that there. I'm going to add in a histogram 2D object. And just as we did with histogram, I'm going to name these and then point this histogram 2D to this histogram 2D data object. So histogram 2D, I'm going to name it new. Oh, you know what? I was most inopportune in my name. I should have called this 2D data. By all righteous accounts, this should be 2D data because it's a data object. By contrast, this should be called histogram 2D. Okay. I'm feeling I'm living on borrowed time because for the past hour and a half or so, the universe has been acting up in a way. And we saw the beginning of it at the beginning of class, and I was expecting continued tribulations, but thus far we seem to have escaped, but I'm holding my breath. Okay, so this is going to be called new infections over time. And we need to refer here to none other than this 2D data structure. And again, autocomplete is your friend. Now, there's also a set of options down here, like involving the chart area, etc. But the most important ones are actually going to be up here with this bins versus envelopes. The envelopes would let us characterize as sort of successive contours around the median, characterizing the contours within which a certain fraction of the realizations of the runs again and again if the model fell, or the values to be plotted there. And in fact, if we were to go here, these envelopes specify that, and I could add another envelope, 0.95, for example, 95% of fall in there, or 97.5, what have you. Okay, so I changed this to show bins. You notice there's two options there. Now, this is likely to require some further frobbing, amongst other things, the x-axis value range should really go from 0 to 365, and I think I'll make the number of intervals 365 here, 365 different intervals, each displaying a day. And I'm not going to set this X value range. So maybe I will set it from 0 to 10, something like that. And I'm going to make it 10 bins. Okay. But again, what we've been setting up here is but the ability to display that. The real action, a key element of the action will take place here again. We have to suck data out of our main and put it into this 2D histogram. Okay, well, the universe exhibited interesting behavior, rather unexpected behavior here. It handed me a window that I did not request, but far be it from me to look a gift horse in the face. Okay, so, oh, I see it. It handed me the very thing I was trying to open in another way. Well, okay. So here, we're going to go to main, and you'll notice we have a data set in main. You may or may not recall this data set, but when we had a new infections reporting event, we added successive daily infections, the count of daily infections into said data set. That data set was then used up here to display the number of cases occurring over time. And if we were to go run one of these, maybe we'll just run the model and rather sort of on the simple baseline scenario. Go. Incident case count. Well, these are the cumulative infections per person. The incident case count is not evident. And what I'm seeing is a little bit unusual in its rendition. Uh, it exhibits ataxic behavior of a rather untoward sort. Let me go see what's going on here. It's almost as if it's rescaling things uh, within a certain range. I'm going to copy this and I'm going to go sleuth and see what's going on here. Okay, so it's saying incident case counts. Well, yeah, so okay, so okay, so it is running, it is having 0 cases after 3,000 so on days. I think I will go and I will have this run for 365 days in the baseline, stop at specified time, 365. And I'm going to run this here and here we go. We may also be dealing with, okay. So very clearly people are being infected here. We're having a rather ataxic behavior still. Cumulative infections per person is 1.3. The total cumulative infections were 333 across the population. The prevalent case count here looks like it was set to, I see that this is a rather unhelpful axis. I see what's going on. And this is also a rather unhelpful axis. It's almost like it's choosing the axes in a very unhelpful way. Okay. I have a theory as to why this was. Let me see if I can remedy it. The prevalent case count here, I think we're dealing with a population size of 250. I'm going to have a population case count here for this window of, so this could be a time window. I see. Okay. So I think we had set it to be rather expansive. The fox shows its tail. It was updating every 1 second. Now, I'm quite certain that that was not there originally, which is probably came in when I had to hack the model in order to run in this version of AnyLogic. But that was one of many tribulations that I had to undergo as I was preparing for class for reasons that on which I won't expound. Okay, I'm setting this to be recurrence time 1 day, and I'm setting this to be for 365, and please forgive me for the rather poor nature of this presentation. Okay. Oh, the time unit is hours. Okay. I see what's going on. So we have kind of competing time windows here. Okay, so I'm going to set this to be 365 days. This to be updating every day, 365 days, cumulative count of infections, and incident case counts. Instead of updating every second, which seems unnecessarily burdensome to say the least, I'm going to update every day. What a nice thing. Okay, well, it's rather pleasant. And here we have do not update data automatically. Okay, here we go. Let's run this. And we are here, exposing people. Here's our prevalent case count. Here's our cumulative incident. And here's our incident case count. We evidently, with incident case count, did not set, we set it to 365 days. But I think the issue is that it's being, okay, here we go. Initial infection event and new infections reporting event. It should be going off every day at 0 days and then 1 day, etc. Okay. So apologies. That was a little bit of a divergence, but at least it has now gotten us the where we need to go in terms of display. Okay. Good. So let me just run this one more time and we'll make sure that everything is hunky-dory. There we go. Cumulative infections and incident case counts. I still am not sure why incident case counts are showing in a time window that is quite so expansive, because I would have expected it to be every time window of days. Maybe it's displaying as a time window of hours. Okay. Well, okay. So let's turn our attention to the remaining objective here. So I'm going to close this one here. So yeah. Okay. So let's go. So the stochastic sensitivity analysis, and let's go here. After the simulation run, we are going to do a similar thing. We're going to have new infections, histogram, 2D data. We're going to add in this data set within main. What is the name of that data set? That data set is new infections data set. Here, right here. I see, yeah, because it's using time as the horizontal value, and that's measured in hours. That's why. Okay, well, here's our new infections histogram 2D data. We're going to need to add it to that. So here we go. So we're going to add root new infections. So we're referring into main again. New infections data set. We're going to add it in here. And there's going to be this somewhat of an anomaly because it's the data set is recording once a day, but it's using time as its X value. And I think I will remedy that a little bit later. So here we're running it again and again. And what we see is successive samples a days in terms of these different hourly values. That's really not what we're seeking, and I'll remedy that here in just a second. It's an unfortunate thing. I should have chosen more artfully. Okay, so how are we going to do this? Well, instead of having time as the horizontal value will be time. Yes, it'll be the current value of time times or divided by 24. So it's 24 hours per day. So this is gonna, if time is 24, it'll be 1 day. If time is 48, it'll be 2 days. And the vertical axis value here will be given later. I put this here. We actually don't need to put something here. Excuse me. I was getting ahead of myself. We'll just say use time, no. we will fill this in when we put the value into it, which is right here. We're going to add in time divided by 24 here. This is where we're putting something in this. So instead of having this data set automatically say, I'm going to add time to every value added to me, I'm going to add time in, I'm going to explicitly add in pairs of times and particular values for them. Okay, so we're going to run this. Okay, so now we're seeing something here, but only for a small range of values. And we have to go figure out why that is. Well, let's go here. Sorry, let's go here. And what we're displaying for the X value is from 0 to 365. So that's what I would have expected. Going from 0 to 365. And so I would expect values out here. I'm going to copy this and I'm going to see if I can diagnose what's going on here. There we go. Okay. So new infections over time. What's the biggest one? It's 10. It's 10. Those are the bins. These are the values. Okay. Okay, so the idea is that perhaps, so one hypothesis is that beyond this, there are no infections, but then I'd expect this to be 0. And I'm not seeing 0 here. I'm just seeing no data at all. These should sum up to 1. If we sum these up over this entire frame. Oh, 0.86. Okay, so some values fall outside of those ranges. So another hypothesis is maybe it went outside of that range. Maybe it's too far above that range. But so that could be. Let's go and we will alter this to have a value for the Y range between 0 and I'm going to give something much larger. I'm going to give 0 and 50. I say 0 and 100, sure. And I'm going to say 100 intervals here. I'm going to run this thing. Okay, once again, I'm seeing this reach some values. Now it's going to be a much wider thing because it can go up to much higher values. I notice that there are some up here at 16 there. After that, it seems to be 0. Okay. So I am torn between two hypotheses about what's going on. Hypothesis 1 posits that there are no new infections taking place after that. Hypothesis 2 posits that, in fact, there are infections. It's just not properly recording them. This is time 15. It looks like it's the last time where there's a material number of infections recorded. So is it possible that this is, in fact, dying out there? Well, first of all, let's go run an example simulation and see what the observed behavior is. Okay, here we go. Okay, so this is paused, so let me resume that. Okay, here's 365. This is the prevalent case count. This is the cumulative infections. This is the incident case counts. You notice the incident case counts are indeed quite small. There's only 16 samples. Aha, the plot thickens. There's only, so almost certainly this is why. First 16 days, we have some infections occurring. After that, it's not recording anything. Okay, so let us go and press ourselves to the task of figuring out what's going on. Okay, so here, recurrence time is 1 day. This should be firing many times. Each time it should be adding it in and resetting the number. So what could be going on? Well, let's go right here. So new infections reporting event fired at time. I'm going to print out something when this is firing, and I'm going to observe, is it in fact firing? My hypothesis is, one hypothesis, this is not firing. Another hypothesis is this does not have the capacity to store something above a certain size. And so it's losing the capacity to store all the items. Here we go. Okay. So I think there's something wrong here with the recording. This time it just died out. This time I think no. It looks like we're getting bombarded by, I'm exposing somebody. I'm recovering, was infected. These are rather unhelpful at this juncture, so I'm going to search for trace LN, and I'm going to comment out the others. Here we go. That's the one I want. Let's go here in state charts, and I'm going to comment out the others. Here we go. I'm going to comment those out. Commenting that out. I thought there was one for recovery too. It's called trace, not trace LN. That's weird. Okay. Okay. Let us go run this. Let's go see what's going on. Okay. We have this. Somehow our case, this is not recording, be on time. And it says, okay, it was fired at time 3. Okay. The fox has shown its tail. It's running for 360 hours, 365 hours. Okay. Okay. So, here we go. This is why. This is the danger of operating when you have multiple time units and you forget the model's time units are in hours. So I wanted to run this for a year, 365 days. I had forgotten the model's time units are hours. Okay, 365 is what, 8760, was it, or something like that?
Okay.
Is that right? Calc, so 365 times 24, 8760. The old horse knows the way. Okay, fine. Okay, you want to, okay, well, that what it lacks in inspiration, it makes up for in satisfaction of knowing where the problem is. Beware when part of you wants to specify in a one-time unit and part in another. Okay. So now we're running this thing for 8,760 hours. Okay. So I should have, yes, there. Okay. Let's run it. Now each one is going to take longer to run. The cores are working. You can see each one of them is profusely spewing out trace LN messages in a manner that is not completely helpful. In fact, is somewhat distracting. We don't really need those anymore, so I'm going to go remedy that. They serve their purpose, a purpose that was at once noble and useful. So I'm going to comment it out, and we will move on. Plow forward. Okay, here we go. Let's go run that. Okay. So here we have our characterization of dynamics over time, summarized across many runs. And one thing you can see, it's perhaps not incredibly high contrast, but you can see that basically there's variability here. As time goes on, there's a larger fraction that have died out, and therefore they lie between 0 and 1 person infected. By this time, it's about 20 some odd percent, about a quarter. Early on, there's basically almost none that have no one being infected per time unit. By the time you get out here, a growing number of sequences of infection of runs have led to no cases of and have died out. Basically, have led to a situation where the infection is no longer circulating. Hence, this has a larger count down here. Now, this scaling is not too helpful. This is all kind of compressed between, it looks like roughly, it looks like there's nothing really above 30 or so. So what I'm going to do is at my one of my last actions here for this is going to be going here and changing this to go from 0 to 30. And so we just have a nicer display character. And I think here it's going to size according to here we go. Okay, so you could see it more clearly here, right? Here's a growing number that have died out by this time. So as it goes on, there's an increasingly evident bimodal distribution. It's zero heavy increasingly as you go forward. About roughly 20% of runs, by the time they reach this last quarter of their operation, they've died out, 15 to 20%. By contrast, there are a fair number that have remained active, and some that even reach as far up, you could barely see it, far up here as like 15 or 20 people being infected potentially. There's, yeah, like there's one or even sub up here. Again, this is not the best way to display it. I would, again, suggest availing ourselves of a spreadsheet to be able to look at this with more clarity. You can see something about it with greater clarity. You notice these numbers here start the number of realizations, which in early time points have no cases of on a given day, is very small, but then it becomes quite a bit higher by this later time. Okay, that's all we have time for today. I apologize. There were some problems with running this model in this version of AnyLogic, and the other one wasn't saving, so I had to hack the file, and I think that caused that seconds problem, etc. But hopefully you got a chance about me, how I went and localized the nature of some of the problems that I encountered and fixed them. That's all we have time for today. I will look forward to seeing people tomorrow, and I will have to repair immediately to my office as someone is waiting for me there. Take care.